So today I am going to talk about generation of high DC voltage. You remember that earlier uh, we have discussed about generation of high AC voltage, and there we discussed two different topics, two different ways of generating the high AC voltage. One is the testing transformer. The second one I discussed was the use of series resonance circuit. Now, so far as the generation of high DC voltage is concerned, we all know that a long time back, HVDC was used to be generated with the help of the electrostatic generators. For example, the well-known Van de Graaff generator. But later on, when the rectifiers came, then the HVDC is generated from high voltage AC through the rectifying circuits. Now there are two types of rectification scheme that is being used for high voltage circuit. One is called asymmetric, the other is called symmetric. So again I will discuss two different types. Although on your screen you can see asymmetric, but I will start with the symmetric first. So I'm going to the symmetric one. Okay, so now you can see on your screen symmetric voltage doubler circuit. It's a very simple circuit. In fact, anybody can understand. What we have a single phase low voltage source here, and then this is connected to the primary of this step-up transformer. The secondary of this step-up transformer is generally of higher voltage rating, depending on what is the target output voltage. Typically, we call it a symmetric voltage doubler circuit. Now, why it is called voltage doubler, that I will now explain. As you can see, the circuit comprises two diodes and two capacitors. It is as simple as that. And then this particular terminal at the bottom of C1 is grounded. So that is the reference potential point. So you can clearly see that since this is an AC voltage, so the polarity will be alternating every half cycle. So when the polarity is such in that particular half cycle that in particular half cycle that just think about the secondary, don't consider the primary, secondary of the transformer. When the right side of the secondary is positive and the left side of the secondary terminal is negative, what will happen to diode D1? That will become forward biased, and therefore the capacitor will be charged in such a manner that the upper plate of the capacitor will become positively charged and the lower plate will become negatively charged. But this is only for one half cycle. In the next half cycle, the left side of the secondary becomes positive, the right side of the secondary becomes negative. The moment it happens, when the left side of the secondary is positive, the diode D1 immediately becomes reverse biased. Whereas when the left side of the transformer is positive and the right side of the secondary is negative, the diode D2 becomes forward biased. So then what happens? This C2 gets charged, and as the polarity is such that D2 is conducting, the upper plate of C2 will be positive, the lower plate will be negative. Now, this is so far as the polarity is concerned. Then the next question comes that what will be the voltage up to which this C1 and C2 will be charged? The answer is very simple, that what is the peak value of the secondary voltage of this transformer? C1 and C2 will be charged up to that peak value. So if it is Vm, then both C1 and C2 will get charged up to a voltage of Vm. And depending on, as you can clearly see, the polarity of the charging of C1 and C2, the two voltages of C1 and C2 will be additive in nature. And therefore, if you take the top terminal of C2 and the bottom terminal of C1, the net output voltage that we are going to get is 2 Vm. That's why it is called voltage doubler circuit. Then you can ask me a question that why it is called symmetric voltage doubler circuit. Now for that, the answer is that you can clearly see that in both the half cycles, the conduction of the diode and the charging of the capacitor is same or identical. Therefore, it is called a symmetric voltage doubler circuit. Now, as far as the voltages are concerned, the junction point of C1 and C2, that is not at earth potential. There it is at a potential of plus Vm. Whereas the secondary voltage is AC and it is of polarity changing 0 to Vm. So at one half cycle, when this secondary voltage polarity and the junction point polarity, they oppose each other, the voltage becomes 0. And when the secondary voltage polarity and the junction voltage polarity are additive, it becomes 2 Vn. So therefore, the left junction of D1 and D2, that does not have a DC potential, that has an AC potential varying between 0 to 2 Vm. This is an important point. And the important point is that the junction point of C1 and C2 have, say, DC voltage of Vm. So what does it mean? It means that this particular transformer you cannot use with, or rather placing it on the ground, because the secondary terminals are not earthed. This is one important point. Second important point is that what is the peak inverse voltage? I think, or I hope that you know what is the peak inverse voltage of a diode. So you can clearly see that the peak inverse voltage of D1 is naturally the highest voltage of the junction terminal of D1 and D2, because the other terminal is R, and that highest voltage is 2 Vm. So the peak inverse voltage of D1 is not Vm, but it is 2 Vm. In the same way, you can analyze the peak inverse voltage of D2. You will find that it is also 2 Vm. Now, apparently, there is nothing special in it. But please remember that if my output voltage is 200 kV, so then Vm will be 100 kV. But then please remember that this D1 and D2 peak inverse voltage will become 200 kV, not 200 volts. So therefore, a big question that comes is what type of rectifier we are going to use here. Because you know that the ordinary silicon rectifier, or for that matter, there is another one called selenium rectifiers. They are all solid state rectifiers. Previously, if you read the books which are written at previous, older days, you will find that the vacuum tubes were used as these rectifiers. Well, vacuum tubes were able to withstand very high voltage. In fact, in our Jadavpur University high voltage lab, When I joined in 1985, there was still vacuum tube operating. And I have seen that one vacuum tube was able to withstand up to a voltage of 350 kV, peak inverse voltage. Now you will not be able to see that because those have gone all, non-functional. So you have to replace it. So now we are using, of course, the solid state rectifiers, but that I will discuss a little bit later. Now, as I have told you earlier, that if my output voltage is say 400 kV required, then each diode peak inverse voltage becomes 400 kV. But that's too high. It will be very impossible, really impossible to make such diodes. So just like that AC transformer case, testing transformer case, we go for a cascade connection here also. How do we do this cascade connection? Again, it is something like this, that we have this low voltage AC source, as you can see, through the middle, and this low voltage AC source goes to the primary of transformer T1, and then you can see D1, D2, C1, C2. That makes one module of this doubler circuit. Similarly, D3, D4, C3, C4 makes the second module of the doubler circuit. What we are doing is we are connecting the two doubler circuits in series. That means the top terminal of C2 will be connected to the bottom terminal of C3. Then all the four capacitors come in series. But then issue comes that the primary of the T2, which is the feed transformer of the second module, it gets its low voltage supply. Whereas if you look at the voltage of the junction terminal of D3 and D4, that potential will vary from 2 Vm to 4 Vm. So 200 kV to say 400 kV. But if the primary is having only a low voltage, let's say 500 volt supply, the insulation requirement will be enormously high for 400 kV. We don't do that. What we do is that typically we use T1 and T2 as the same transformer, identical transformer. You can ask me what is the advantage in that? Well, advantage is pretty obvious. Advantage means if by any chance, due to some reason, one of the transformer gets faulty, then the other transformer and that particular module will be still operating. That means instead of 400 kV or 4 Vm, we will still get 2 Vm. So we want identical transformers just for interchangeability of the transformer. So to do that, we need an additional transformer, which is called intermediary or isolating transformer T3. This is simply a 1:1 transformer. So voltage rating is same as that of the low voltage side, but the insulation between the primary and the secondary will be for 2 Vm. So therefore, what will happen? The insulation between primary and secondary of T1 will be 2 Vm. Insulation between primary and secondary of T2 will be 2 Vm. And that additional 2 Vm insulation required will be between the primary and secondary of the T3. So what will happen? The low voltage source is connected to primary of T1 and then primary of T3. Then 1:1 transformer means the same voltage is applied to the primary of T2. So that's how the entire circuit works pretty nicely. But then if you look into the literature or books, you will find that there are a lot of questions about why should we use a third transformer. Can we not do something with two transformers? That actually makes the overall things much, much simpler. Yes, we can do that. So there is another circuit for that. This is called the improved symmetric voltage multiplier circuit. So what is being done here, you see, is more similar to that our cascade connection. That the primary low voltage AC source is connected to the primary of T1. In this case, both the transformers are not two-winding transformer, but it's a three-winding transformer. That means there is a tertiary winding in addition to primary and secondary. The voltage ratio is such that between primary and secondary, we have that large voltage ratio or turns ratio, whereas primary and tertiary, that means 1 and 3 winding of T1, they will have 1:1. So if I apply 100 volt to primary of T1, then that will be increased up to say 100 kV on the secondary, but at the tertiary it will be still 100 volt. And that 100 volt goes to primary of T2, and again another 100 kV is generated in the secondary. Now what is the advantage in it? Yes, advantage is pretty obvious because the transformer T1 has an insulation of 2 Vm between its primary and secondary and tertiary, because it requires 2 Vm insulation. Similarly, primary of T2 has a 2 Vm insulation with respect to secondary and tertiary. And since primary of T2 is connected to tertiary of T3, so the overall insulation of the transformer T2 with respect to the low voltage source is still then 4 Vm. So it can work therefore perfectly well. So here also we can have two identical transformers, and then we don't require a third transformer, and everything looks good. And the rest of the thing, you know, the bottom D1, D2, C1, C2 makes one module, D3, D4, C3, C4 makes one module, and then all the capacitors are in series, so we get a multiplier circuit. So depending on how many modules we are connecting, we will get 2 Vm, 4 Vm, 6 Vm, and so on. But generally we don't go more than 3 modules because there are a lot of other problems that come if things become too large. So all these things have been explained in this note, which is obviously not very difficult for you to understand. But then a question that people asked, not now, long time back, that can I have this circuit with one transformer? Because transformers are very, very expensive if it is high voltage transformer. It is really expensive. So can I do it with one transformer? The answer is yes. So a very simple circuit is proposed here, which is, you can see, is a half-wave rectifier circuit. Now, here it is clear that you know that in the half cycle, when the top terminal of secondary is positive, that means terminal A, then diode D is forward biased, and then capacitor C is charged, and C is charged in such a way that the upper plate will be positive, lower plate will be negative. And the voltage up to which this C will be charged will be Vm. But that is only for the no load condition. What happens in the load condition? Because then load means here, please remember, it is the test object which we are testing. So resistance RL, although it is not small, but it is still there in the circuit. So when diode D is reverse biased in the other half cycle, what happens to capacitor C? Since there is a resistance in parallel with C, the C will definitely discharge through RL. So the terminal voltage of C, that means the voltage at terminal B, as shown in the figure, will not remain Vm, it will drop. Now how it looks like, let me explain it in this way. You can see this is a positive half cycle, then negative half cycle, again positive half cycle. So initially, let us say that at the very beginning, the capacitor C gets charged and it gets charged up to Vm. And that happens when the positive half cycle peak is reached. And you know when the charging is complete, that the current will be 0. Current means which current? The charging current. So that happens at 90 degree. After that, what happens? After positive peak, the potential of A goes down because it is AC, whereas the potential of terminal B remains at plus Vm. So diode D is forward and reverse biased. So you can see in this figure that after theta is equal to 90 degree, the diode D is reverse biased, but then it starts discharging. So the voltage starts dropping. Of course, this diagram is not correct. It is actually an exponential drop, but not a straight line. But then you ask me why it was drawn as a straight line. Yes, that answer is very simple again, that you know the discharge time constant of a capacitive resistive circuit is R into C. This C is typically of the order of a few microfarads, but this RL, being insulation resistance, will be of the order of maybe hundreds of mega ohm. So this time constant becomes quite high. It might be 100 seconds. Whereas this half cycle of a 50 Hz is 20 millisecond. Whereas the time constant of discharge is, let's say, 100 seconds. So what will happen? With respect to 20 millisecond, it looks like almost a straight line instead of a exponential curve. So it goes dropping, dropping, dropping. This voltage shown as VB. Then entire negative half cycle, diode D is reverse biased. And then in the positive half cycle, again the voltage starts increasing. That means the potential of terminal A starts increasing. But still, you see, up to a certain theta, the VA, that is the supply voltage, is still less than VB, which is after discharging, whatever the potential of terminal B. At a certain theta, these two, that means supply voltage, which is at the terminal A, and the potential of B, which is due to the discharge, they become equal in the next positive half cycle. And only from that theta, the terminal voltage A becomes higher than the terminal voltage B, and the diode D becomes forward biased again. And therefore, from that particular theta, as you can see here, when this VA, that means the sinusoidal voltage, and VB, which is the voltage of the capacitor, being equal, after that, that sinusoidal voltage is higher, so diode D is forward biased, and diode D again gets recharged. And recharged up to what? Of course, to the peak value of the sinusoidal voltage, Vm. And so every half cycle, that positive half cycle, this is going to happen. So the diode D will conduct not for the entire half cycle, but for a specific angular duration, depending on, of course, what? Depending on the value of C and depending on the value of the load resistance, because that determines the time constant of discharge. Now, so far as the current is concerned, you can see the current is flowing through this diode and naturally through this transformer is only during this period of charging. So there is no current on the negative half cycle. There is only a small amount of current through the transformer and diode in the positive half cycle. That's why it is called asymmetric voltage, or rather the asymmetric circuit. So this asymmetry creates certain problem that, it might cause core saturation if this current gets higher because of some load resistance. Because if it is only at one half cycle, then and moreover this is a DC current in that particular half cycle, so there is no MMF balance between primary and secondary of the transformer. So a very special transformers are required, which is again not very a good decision. So then people thought, let us use the full wave rectifier, As you can see here, this is a very clear full wave rectifier circuit, but this is hardly used in our high uh, voltage generation. Reason is that for this you need a center tap transformer, and that is what we don't prefer in high voltage circuits. We always prefer that the bottommost terminal, that is the lowest voltage terminal of the transformer, should be earth, not the center point of the transformer. So theoretically, figure 27 on your screen is perfectly okay. It can be used, but for all practical purposes, we don't use it. So then what can be done? This has been a circuit which has been developed long time back, 1932. So only 90 years back, this was proposed by two scientists, Cockcroft and Walton. So it is still today known as Cockcroft-Walton voltage doubler circuit. It is again using two diodes and two capacitors as shown on your screen, but it is only one transformer, not like the symmetric circuit where two transformers are used. Now how it works, first let us take open circuit condition. That means on the right side, consider that this load RL is not there. Then what happens? When the bottom terminal of the secondary is positive and top terminal of the secondary is negative, then diode D1 becomes forward biased. So C1 gets charged in such a way that the right side plate is positively charged and left side plate is negatively charged. And what is the voltage up to which C1 will be charged is of course the peak value of the secondary voltage, which is Vm. So when this one half cycle is over, C1 is then already charged up to a voltage of Vm, and as the polarity is shown. Now what happens when the next half cycle, when the terminal C becomes positive and terminal O or terminal A, whatever it is negative, then D1 is reverse biased. But then the polarity is such that the EMF direction is from bottom to top in the secondary, and the polarity of C1 is also from left to right, so they are in additive mode. And as a result, diode D2 is forward biased and the C2 gets charged, and charged in such a way that the upper plate is positive, lower plate is negative. What is the voltage up to which C2 will be charged? That's again obvious. That is the peak value of the secondary voltage plus whatever be the voltage of C1, and under no load condition this is Vm. So it will be Vm plus Vm. So C2 will be charged up to a potential up to Vm. So if we take the potential between ground, which is the bottom terminal, and the terminal D, we get 2 Vm. Now why it is called, or rather why it is better than the other circuit, that half-wave circuit? See here, both the capacitors are getting charged in both the half cycles. That means in one half cycle when D1 is conducting, C1 is charged. The other half cycle D2 is conducting, C2 is charged. So in both the half cycles, there is a current conduction through the transformer secondary. So therefore, the current through the transformer secondary is not unidirectional, but it is in both the directions. And that is the biggest advantage. But why it is not symmetric? Well, that will show that the current in both the half cycles are not identical in nature. So therefore, it is called asymmetric voltage circuit. Then naturally you can ask me a logical question that if the currents in both the half cycles are not identical, and then you can always go for its analysis, Fourier circuit analysis, and then Fourier series analysis, and then you can find out what are the components. And you will always find that there might be a small DC component, but that will be very small. So ignoring that part, we can say that this does not have that problem of DC component of current flowing through the transformer, but it has one problem, that the currents are not asymmetrical in the two half cycles. Coming to the loaded condition, that means not open circuit condition, but the loaded condition. That means parallel to C2, we have connected the test object, and the insulation resistance of the test object is RL, which might be, again, I repeat, of the order of 100 megaohm or even more. But the moment I say that, that discharge of C2 starts playing a role, because please remember that the terminal D gets charged up to a 2 VM when this secondary of the transformer has VM in addition to the potential across C1 as VM. But immediately after that theta, the secondary terminal voltage goes down, and immediately the potential of terminal B is no longer 2 VM. So even in that half cycle, after that peak voltage, the diode D2 will not be forward biased, it will be reverse biased. So this C2 will be discharging for a quite significant amount of time through RL. But as I said, the time constant will be considerably higher compared to the 50 Hz, that one cycle, which is 20 millisecond, half cycle is 10 millisecond. So how does it look? Let us again go into this waveform diagram. So again, we say that initially, let's say that there is no RL, C2 is charged up to 2 VM. Now I connect the load. So what happens? The C2 is charged up to 2 VM when it will be always at the peak value. So start from that peak value. Then what happens? Please remember this voltage at the terminal D is now at 2 VM. So all other terminals are at a lower voltage. So the left side, all these diodes are reverse biased. So C2 starts discharging. So now see, there is a curve which is VD at no load. By the way, let me just explain what are the two sinusoids here. The smaller sinusoids of magnitude, peak magnitude plus Vm is nothing but the transformer secondary voltage. Then what is the other sinusoid which is varying between 0 to 2 Vm, which is quite obviously the potential of terminal B, because it has a potential of Vm across C1, which is a DC voltage, and it has a AC component of the transformer secondary, and they are additive. So plus Vm goes up to 2 Vm, but when the transformer secondary is in phase opposition, it will be 0. Therefore, the second sinusoid, you see, it varies between 0 to 2 Vm. It is nothing but the potential of, as I said, terminal B. And then the solid line is nothing but the terminal at the output terminal voltage. So starting from this theta is equal to 90 degree, when it reached its maximum voltage, which voltage? That is the voltage across C2. That is the output voltage. Then it starts decreasing because now all this diode D2 is reverse bias. So C2 is discharging through RL. And therefore you can see it starts dropping. But then something interesting happens, that see what is happening to D1. See what is happening to D1. What happens is when this D2 is reverse biased, this C2 is discharging through RL. The point is this RL being 100 mega ohm and D2 is D2 is reverse biased, but then it has some resistance, right, in its reverse biased condition. So C1 is finding another path that through D2 and RL. But now, when that happens, so just I will try to say that this C1, it will not remain exactly Vm, because when these diodes are reverse biased, because this RL is almost comparable to the reverse biased resistance of D1 and D2, the C1 also discharges through the reverse biased resistances. So the voltage of C1 doesn't remain plus Vm all the time. It goes down a little bit. So at a certain point in the half cycle here, let me show again. So at a certain point in this half cycle, that so-called negative, when D1 was actually conducting before theta is equal to 90 degree, at a certain point when this terminal A or O, that becomes higher potential than the terminal B, because C1 is not at Vm, it has gone down slightly, and therefore just before theta is equal to 90 degree, this voltage across secondary becomes equal to the voltage of C1 and then becomes higher. So then for a short duration of time, from theta is equal to, let's say, 85 degree to 90 degree, this D1 conducts. Even then, D2 is reversed bias. So there will be a small current when D1 is on before theta is equal to 90 degree in the negative half cycle. But a very interesting thing happens that moment this D1 is conducting, what is happening to C2? The C2 is finding that there is a high resistance on its right side through RL, and on its left side, it has a very high big reverse resistance of D2, but then D1 is forward bias, so no resistance. And when both are reverse bias, then on the left side of C2, there are two reverse bias resistances. But now, when D1 is conducting, when in this negative half cycle for a small time before theta is equal to 90 degree, D1 is conducting. So it has only the reverse bias resistance of D2 on the left side of C2. So now they come in parallel, D2 and RL, and therefore there is a sudden drop in resistance parallel to C2, and therefore time constant changes. So from, let's say, 85 to 90 or 82 degree to 90 degree, there is a sudden drop in slope because it is discharging at a faster rate. But then what happens? That in the negative half cycle, after theta is equal to 90 degree, then C1 is again charged fully up to Vm, and D1 becomes reverse biased. That means after this small time duration, again D1 is reverse biased. So then again, the left side resistance of C2 is the reverse resistance of D2 plus D1. That means 2 times. So that change in slope of the curve again goes back to its original slope. So from theta is equal to 90 degree on this curve in the higher, that larger sinusoid, up to a certain point of theta is equal to, let's say, some 80 degrees on the negative half cycle, you get a one slope. Then from theta is equal to, let's say, 80 degree to 90 degree, you get a higher slope. And then again, you get a relatively lower slope, and it goes on. And then in the next half cycle, there is a point which I have already discussed, that if again, which one? That the potential of B becomes higher than D because C2 has discharged. So C2 will again get charged. But wait, the big question is whether C2 will be really charged up to 2 Vm. The answer is no, because this C1, when D1 is reverse biased, it will discharge through D1 a little bit of charge. It will also discharge through RL. So effectively, the actual highest voltage of C2 is never 2 Vm. It is called Vd max. That is the maximum value of the output voltage. And the lowest voltage is, of course, at that point on the positive half cycle when C2 starts charging. And that is called VD min. So therefore, this is the ripple of the output voltage. And the DC value is nothing but VD max by plus VD min by 2. So there are two voltage differences here. One is del V1. What is that? That is from 2 VM to a slightly lower voltage. Why this happens? That is because C1 is losing its charge, so that C1 is losing its charge, so that C2 is not going up to 2 VM. And there is a second voltage difference del V2, which is actually the highest value across C2 to lowest value across C2, and that is because of the discharging of C2. So del V1 effectively comes because of charge loss of C1, even if we don't say it is discharging, but charge loss of C1 over the reverse resistance of D1 and also through D2. Del V2 is purely due to the discharge of C2. So therefore, if we find out the expression, then what is the average DC output voltage? I have already said VD max plus VD min by 2. In the diagram on the right side, you can see VD max is the peak value of the output voltage of C2. VD min is the lower value or the minimum value. Now we try to find out what are these two voltage differences, del V1 and del V2. So first we say that let I be the load current. Load current means the current flowing through the resistance RL. This is the load. How do we find it? It is quite very simple. That what is the maximum energy of C2? That is half C2 VD max square. What is the minimum energy? Half C2 VD min square. And this energy has been discharged. So if I say VDC into I, and for how long it has discharged? T2. And what is T2? Then we can, from the curve, we can see this is T2. That is from theta is equal to 90 degree of the previous subcycle to theta is equal to, let's say, 80 degree of the next positive half cycle. That is T2 when capacitor C2 is discharging because of the diode reverse bias. So if you do the algebra, you will find that del V2 comes I, where I is the DC current, that is the load current, T2 by C2. Now since T2 is almost equal to T, which is the time period, because this T1, that means the time when this diodes, when this capacitor C2 is charged is only for about, say, maximum 10 angular degrees. So we can take T2 is equal to T so that it can be correlated to F. So del V2 is I into time period by C2. So it becomes I by frequency into C2. That's how the equation is developed. Now, this is not the exact equation. If you want the exact one, you have to do the circuit simulation through some simulation software. Then we get the exact value. But for the, simple calculation, this is quite good. Then C1 also loses its charge. So how do we find that charge? And I said that C1 loses its charge over the diode D1 at the same time over the diode D2 during their reverse bias condition. And that happens over the entire time period. For some time over diode D1, for some time over diode D2, reverse resistance. So we say that this current I is dq dt, which is C1 dV dt. But then dV means that change in voltage across C1, that is del V1 by, and dt is the time period. So we correlate this as del V1 into I into time period by C1 or 1 by FC1. And then we put the average DC output voltage, and then we put all these expression what we have developed here. We find an expression for the average DC output voltage. And we can clearly see that they are naturally related to the value of C1 and C2, but they are also inversely related to frequency. That means if frequency is higher, the voltage drop is lower. Now you can ask me, why is it so? The answer is very simple, that if the frequency is higher, then the time period is less, because for 50 Hz it is 20 millisecond, and if it is 1 Hertz, if it is 500 Hertz, it will become 2 millisecond. But this time constant of the discharge circuit, that remains 100 second because of the value of C2 and RL. So if the time period reduces, then the solid line, as you can see, that is the discharge of C2, that will be much less because the time is much smaller for discharge. That's why it is inversely proportional to the frequency. So a problem is given here. So you can see what is stated. A Cockcroft alternate voltage circuit is used to test a cable at 170 kV. The insulation resistance of the cable is 6 into 10 to the power 9 ohm per meter. Per meter means per meter length of the cable. And the length of the cable is 12 meters. Stage capacitances are both 0.1 microfarad, that means C1 and C2. The generator is supplied from a voltage source, 230 volt by 250 kV testing transformer. And this is the beauty of this second circuit, why it is so popular, that you see we need only one transformer here. So the testing transformer, which is used for AC voltage generation, can be used for DC voltage generator by simply connecting the capacitors and diode. So you don't require two different transformers for DC and AC, and that is a huge cost and operational saving for the lab. So how do we solve this problem? Frequency is 50 Hz. So given C1 and C2 known, RL is per meter this, but this is a cable and this is the cable insulation resistance. So just visualize that cable insulation resistance is between the cable conductor and the cable sheath, between the radial, you think about the coaxial configuration. So these resistances are between the cable conductor and the sheath. So if the length increases, more and more resistances are coming not in series but in parallel. I repeat, these insulation resistances are between the central conductor of the cable, which is cylindrical, and the sheath of the cable, which is also cylindrical. This is insulation resistance. So as the length of the cable increases, more and more such resistances between the central conductor and the sheath are coming in parallel, not in series. So as the length of the cable increases, the insulation resistance of the cable decreases, does not increase. Please remember this, because this question is very often asked in interview, because this is a very simple electrical engineering knowledge. So in this case, for 12-meter cable, what is the RL? We have calculated here. Then test voltage is 170 kV DC. So what is the current? From the RL and test voltage, we have found out the current. Then already we have developed an expression. So VDC, which is 170 kV. To VM, we don't know what is VM, that we are going to calculate. F is known 50 Hz. C1 and C2 is 0.1 microfarad. So we find VM 85.051 kV. So transformer primary voltage from the trans ratio, I can get this, but please remember this is Vmax, which is the peak value. So typically we calculate the RMS value, which is 55.33 volt RMS. That's the answer. So I hope this is a very simple problem which you will be able to grasp. Now here also, as the requirement of output voltage increases, we go for cascade connection, but remain keeping only one transformer, not multiple transformers. So here is the same one, that one in feed transformer, that from where I am getting the high AC voltage. Then you can see that up to the terminal B, that is A, B, D, this is one module, two diodes, D1, D2, and two capacitors, C1, C2. Then above that, there is another module, D3, D4, and C3, C4. Then above that, there is D5, D6, C5, C6. Then above that, D7, D8, C7, C8. So you can clearly see there are four modules here. So it is called a four-stage multiplier circuit. So every stage has an output voltage of 2 Vm, and we get 8 Vm. But each of the capacitors, each of the diodes, if you calculate, they will have the peak inverse voltage as well as the capacitor rating will be 2 Vm. That's the advantage, that we get output as 800 kV, but each one will have a capacity or rating of 200 kV, which is much, I would say, practically possible to design and manufacture. This is how the potential of every terminal A, B, C, D, F, G, H, that means A, B, C, D, F, G, H, where you can see B, D, F, H, they are all having DC voltage and gradually multiplied. So B will have 2 Vm, D will have 4 Vm, F will have 6 Vm, H will have 8 Vm. Whereas terminals A, C, E, and G, they will have an oscillating voltage. A will be between 0 to 2 Vm, C will be between 2 Vm to 4 Vm, E will be 4 Vm to 6 Vm, and G will be 6 Vm to 8 Vm. So that's entirely thing here explained, and I'm pretty sure that the way it has been written here, as a student of third year electrical engineering, you will be able to grasp that. So then that's the end of it. After that I have the symmetrical double circuit that I have already explained to you. Now what I'm going to do is that in my last class I have shown you some photo, and today also I am going to show you a photo of the real life, what is called high voltage DC generator circuit. Now let me see which one it is. Here. Hope it will come on your screen. Now, if it is coming on your screen, this is again the Central Power Research Institute, CPRI Hyderabad photo. You can see here, this is an 8-stage high voltage DC generator. Now, if I say it is a DC generator, everybody will be so surprised. That generator always gives you some other, image on your mind, that there will be a machine or everything. But no, it's just a capacitor diode configuration. As you can see here, these double rings, they are the stress shields or corona shields, and in between these double rings, we have the diodes as well as we have the capacitors. Typically, if you see between the two columns, there are some diagonal connection. Here you can see, if you see my mouse moving here. Similarly, for all these, you can see there are some diagonal connections. They are typically the diodes. And in between the two double shield, you have the capacitors. This is typically the configuration. And then in the end, we have always the potential divider. That's generally this vertical one, which is, you can see here, there is no diagonal connection. So it's not a capacitor. This right one at the back side. Whereas these columns, they have diagonal connections. So they are actually not, they are actually capacitor vertically stacked. Because, you require a lot of insulation. So between two that corona shields, you have a capacitor, the rest is all simply vertical insulators, giving the required amount of insulation so that there is no problem. So you can see this is the high voltage actually, how it is different from the low voltage circuits. If it is 200 volt, things are of certain nature. If it is 800 kV, things are completely different. So please remember this one as student of our department. I will close today's class with showing you one more photograph which I have found very interesting and very practically relevant. So I'll show you this one. Now it is coming on your screen. Probably you can now see. It is a generator step-up transformer bank. That means that it is a generating station. So the entire power is being generated. Now this has to be transmitted. So if it is, in India, the highest generating unit as far as megawatt is concerned, I don't know whether you know it or not. We have something called subcritical thermal power units. The subcritical thermal power units typically are of the rating 210 megawatt. Then we have we have supercritical generating units, thermal. They go up to 500 megawatt. Then we have ultra supercritical thermal units, which go up to 650 or above megawatt. Typically, we have this Khargon in Madhya Pradesh and others. They have 660 megawatt each unit. One unit generates 660 megawatt. Think of it, one unit. But then the Kundakulam nuclear power plant that we have, there we have one generator generating 1 gigawatt. One generator generating gigawatt. Can you imagine that? This is very difficult to imagine, but then that power has to be transmitted. So that 1 gigawatt or let's say 660 megawatt is coming to this transformer bank. Now, why I am showing it, that you see, this is very interesting because it's a three-phase connection, but you see we have three distinctly different transformers. Why is it so? Because they are not a single three-phase transformer. This is called a transformer bank. Each one is a single-phase transformer and they are externally connected in star or delta. I think you can clearly understand that we can always connect externally in star or delta. There are a lot of advantages in that, because in that case, each one probably will be of 200 megawatt capacity. If the generator is of 660 megawatt, or if it is 1000 megawatt, it will be of the order of 350 megawatt each one. Because it is impossible to design one transformer which is of the order of 700 or 800 megawatt. It's not possible. Or even if it is possible, it is extremely expensive. And if something goes wrong, there will be a tremendous problem. So we go for a lower rating of individual transformers. And the advantage is that if you keep one such transformer in your substation, remember, these transformers are never kept in go down, even if they are not in operation. You know why? Because you can't keep a transformer in cold condition. The winding will acquire a lot of impurities and particularly moisture. So what is done, even when they are not in operation, they are connected to the line, so they remain charged, which means the core current, the charging current, or not the charging current, in the magnetizing current flows through the transformer and the transformer remains hot. This is the way we keep the transformer in substation. So what we do, we can purchase 4 transformers of lower power rating and one transformer will remain connected to the line but not in power transmission, and 3 will operate in either star or delta. If we require one transformer for maintenance or one transformer gets faulty, then the other 4th transformer will be immediately connected. As it is external connection, there will be no problem. So the entire power system remains highly stable and resilient. And you can see that there are concrete blocks between the transformers. Why is it so? Because if there is any sort of fire or any sort of problem in one transformer, that will not immediately affect the other one. So they are strictly partitioned by concrete. So this is called a generator step-up transformer bank, which probably later on you will come to see. Now, how do we know it is a step-up transformer bank? Looking at an object, you must be able to identify. This is very simple. If it is a three-phase transformer, then on the top of the transformer tank, you will see 3 bushings. But here you see there is only 1 bushing, this red color. So that means it's a single-phase transformer. So that is another way of looking at it and taking immediately an engineering decision. See, this is a 3-phase equipment, or I can show you actual transformer. Let me see. I have something. I don't think I have it. Anyway, this is how we use transformer banks. That's how we use it. So that's all for today. Thank you for joining.